Hi everyone and welcome back. Today we're going to be covering a chemistry topic called equilibrium or dynamic equilibrium, along with some subtopics such as reversible reactions, the Haber process, and Le Chatelier's principle. So to start off, here we have two different equations. The first reaction says A plus B, which is our reactants, and C plus D as our products. The main difference between these two is that our first one, only one arrow pointing from the reactants to the products. But in the second one, we have the reactants pointing to the products and the products pointing back to the reactants. So what we're seeing here is a forward reaction versus a reversible reaction. What this means is that in a forward reaction, the reactants are going straight to the products. But in a reversible reaction, the products can go back to the reactants. An example of a reversible reaction is in the Haber process. We know that this is a reversible reaction because we have the arrows pointing to the products and back to the reactants. So this indicates that whenever you see a reversible reaction, you'll know because you'll see two arrows facing opposite directions. And once again, this is known as the Haber process. Now I'm going to talk to you about dynamic equilibrium. In dynamic equilibrium, we first need a reversible reaction to happen in a closed system, and at some point, the rate of the forward reaction is going to be equal to the rate of the reverse reaction. And that's going to help you reach equilibrium. Just to reiterate, dynamic equilibrium is when the rate of a forward reaction equals the rate of the reverse reaction in a reversible reaction that's happening in a closed system. But there are also factors that can influence the equilibrium that we have in a system. A rule that can help you understand this is Le Chatliers principle. So what this principle says is that if a stress is applied to a system at equilibrium, the system is going to change in order to relieve that stress and reestablish equilibrium. Now, there are some factors that can impact equilibrium, such as concentration, temperature, and pressure, but only in gaseous systems. Now, when we refer to concentration, we're talking about the amount that we have of something. So if we have a high concentration of molecules, we have a lot of molecules. But if we have a low concentration, we have a little bit. So now I want you to think of a balance scale, where on the left side we have reactants, and the right side we have products. So now let's say we want to add reactants. What's going to happen? Well, the scale that has a reactant is going to start tipping down because it's heavier. We have a higher concentration. So now the scale is going to look something like this. But we want to maintain our equilibrium. We want to reestablish this equilibrium. So what we do is we're going to shift to the products and add more products in order for the amount of reactants to be the same as the amount in the products. That way we can reestablish this equilibrium. Once we add these extra products, we're going to be able to get rid of the excess reactants that we had initially. So if we add more reactants, we have to shift to the products in order to get rid of the extra reactants. Now the same thing is going to happen if we add products instead of reactants. If we add more products, now this side of the scale is going to tip down, and we're going to have to shift to the reactants in order to get rid of the extra products. So if we're shifting to the products, we're shifting to the right, and if we're shifting to the reactants, we're shifting to the left. Now I want you to imagine that you're at a grocery store. Let's say on one shelf we have some cereal boxes that can only hold up to 4 boxes each row. Let's say someone comes up and they buy one of these cereal boxes. Now we have less cereal and we have an extra space to fill. That means we no longer have a full row of cereal boxes. But we can't leave the spot blank or else we're just going to end up with an empty row. So let's say you have a worker at the store who manages the stock. So they come over to the shelf and they're like, oh no, I'm missing a cereal box. So they walk to the storage room or wherever they get their cereal boxes from, they grab a cereal box and they put it back. So now they replenished the cereal boxes. So what happened here is that when you remove a reactant, in this case the cereal boxes, you have to go back to the reactants or you're shifting to the reactant in order to replenish them. And let's just say that these are your other reactants. So after losing one of the cereal boxes, they had to go back to the reactants where they get their sources from, and they added it back. And the same thing is going to happen, but with products. Now imagine this is a different cereal box, or whatever product you want to imagine. Let's say someone comes up to the shelf and they decide to take away one of the products. Now, once again, we have an empty spot to fill. But where did we get that spot from? Well, we go back to the source. We go back to where we actually got it from. So let's say this side of the shelf is your products. If you run out of products, you go back to the stock or where you got the products from. You're going to take one of them, or however much you're missing, and you're going to bring it back. And now the shelf is filled. So if you ever lose a product, you're going to add the product. You're going to shift to the products in order to replenish the products. So this is Le Chatelier's principle. Whenever we interfere with the equilibrium, the system does the opposite of what we do, also known as the forward reaction, and it favors the reaction that goes against what we do, which is a reverse reaction. So let's just bring back the Haber process for just a moment, and we're going to talk about how the equilibrium changes when we add stresses. So here we have our reactant on the left side, and here we have our product on the right side. Let's say I want to add some more nitrogen. Add more N2, which is in the reactants. That means I'm adding to the reactants. This disturbs the equilibrium, meaning that now I have to shift to the products in order to reestablish that equilibrium and get rid of the excess reactants. So I'm going to shift to the products, and that's going to help me get rid of the extra reactants. So what we did is we basically added more, or we increased the concentration of nitrogen. But to relieve that stress of the increased concentration, it shifted to the products. But now let's say I want to decrease the concentration of ammonia, or NH3. Now ammonia is in our products, but if we're taking away from our products, it's minus the products. So now what we do is we actually have to shift to the products in order to replenish the products. Now, the second factor that can influence equilibrium is temperature. So let's refer back to the chemical equation for ammonia. Here we have our reversible reaction, but this time we have heat in our products. Whenever we have heat in our products, this is an exothermic reaction, because in an exothermic reaction, we're releasing heat. However, let's say we add heat, or the system is heated. If we add heat, we're basically adding to the products. So we're simply going to shift to the reactant side, or the left. And by doing so, you get rid of the excess heat. But if the system was cooled, or we're decreasing heat, we're basically minusing the products. So we have to shift to the right, or to the products, in order to replenish that heat that's in the products. So now let's say you have a general equation where you have A plus B plus heat in the reactants is reversible to AB, which is in the products. Now in this case, you have an endothermic reaction because in your reactants, you have heat. If you were to have heat in the products, it would be suggesting that heat is being released. But in this case, an endothermic reaction, we're absorbing heat. So once again, if we were to add heat or increase the temperature, this time we're adding to the reactants because heat is in the reactants. And by doing so, we're going to have to shift to the products or to the right in order to get rid of this extra heat and reestablish the balance. But let's say we decrease heat. We're also decreasing our reactants because they're on the same side. That means we're going to have to shift to the left or to the reactants in order to replenish that heat from the reactants. Now, the third factor that is going to influence equilibrium is pressure changes, meaning the pressure in the closed system is either going to increase or decrease. However, pressure changes only affect the equilibrium systems with unequal moles of gaseous reactants and products. Now, for a reminder, how do we figure out the moles in an equation? Well, all we have to do is look at the coefficient that's attached to it. But if it doesn't have a coefficient attached to it, we're just going to take it as 1 mole. So let's say we have 3H2. That means we have 3 moles of hydrogen. But if we had N2, we would have 1 mole of nitrogen. Now, if we increase the pressure in a system, we're basically decreasing the volume or the space. So let's say this is your regular closed container. If we increase the pressure, we're basically lowering the amount of space that the container has for the particles to interact. As we increase the pressure, we're also increasing the concentration. This is adding more stress, and it's going to result in the equilibrium shifting to the side with the lower total number of moles in order to reduce the number of moles in the container. So the side with more moles is going to shift to the side with less moles. And once there's a shift to the side with the lower total number of moles, the reactants have more space and relieve that stress. For example, let's take ammonia. On our reactant side, we have 1 mole of nitrogen and we have 3 moles of hydrogen. Together, we have 4 moles on the reactants. But now in the products, we have 2 moles of ammonia. So we have 2 moles in the products. That means equilibrium is going to shift from the reactants to the products. So we're shifting to the right if you increase the pressure. But now let's say you decrease the pressure, so you allow for the molecules or the reactants to have more space. Let's say this was the container before and this was it after. There's way more space and more volume, meaning less concentration overall. But if we decrease the pressure, that means that the equilibrium is going to shift to the side with the higher total number of moles in order to increase the number of moles in the container. So with more space and decreased pressure, the particles are going to be able to move around more freely and fill up the space in the container. So it's going from less moles to more moles. I also just wanted to add that this relates back to the collision theory and how the more space the particles have, the less frequent collisions, but the less space the particles have, the more frequent collisions. Last but not least, the presence of a catalyst is also going to influence the equilibrium. A catalyst is going to lower the activation energy and increase the reaction rate. More specifically, it's going to increase the forward and reverse reaction rates equally. Therefore, a catalyst has no effect on a system at equilibrium. All it does is help you get to equilibrium faster, so it's increasing the reaction rate. However, I do want to go back to just one part about concentration. Let's say I'm increasing the reactants. However, when I increase the concentration in the reactants, I'm going to have to shift to the products, therefore relieving that stress. So the products are also going to increase in concentration. And vice versa, the concentration in the reactants now is going to decrease after the shift to the products. So just to show you once more, let's say in our balance scale, on the reactant side or on the left, I'm adding to the reactants. So now the reactant side or the left side is going to be heavier. But in order to reverse that, I'm going to shift to the products or the right side and add or increase the concentration on that side in order to rebalance it.